Hello, welcome to Maths with EJD. In this video, I continue to talk about non-linear programming. And under this, we have seen the penalty method, which penalizes a, it converts a constrained optimization problem into an unconstrained problem, such that when there's a violation, the system is penalized. And then we have the barrier method, which guarantees that solution always lies within the feasible region. So today, in this video, I'll be talking about the KKT conditions. That's the Karush-Kuhn-Tucker conditions, which is actually a generalization of the Lagrange multiplier. And afterwards, we'll be talking about the evolutionary algorithms. And there are couple of such algorithms. I think we'll be looking at five of them, evolutionary algorithms. So we'll be looking at simulated annealing, tabu search, um, and so on and so forth. We'll be looking at five of them up to the particle swarm optimization. Yeah. So penalty method done, barrier method done. Now KKT conditions. So particularly the focus is on KKT conditions with feasibility, with feasibility. So, if there's a condition, the condition can be met or not. So here we are looking at the situation where the KKT conditions are met. But first of all, the KKT conditions they are actually what you can call the Karush-Kuhn-Tucker conditions. The Karush-Kuhn-Tucker, or KKT for short, are essential for solving constrained optimization problems. They provide necessary conditions for a point to be optimal, assuming certain certain regularity conditions, e.g., what's known as the Slater's condition for convex problems. So we already know that convex problems are situations where you can easily find a unique global minimum or global maximum, or it's easy to find those minima and maxima. So let's talk about the optimization problem in this situation, which we have seen a lot, and it is generally to minimize f of x subject to gi of x less than or equal to 0, which are inequality conditions, and then hj of x equals 0, which are equality conditions. And we have that f of x is the objective function. We've talked about this a lot. F of x is the objective function actually. And then you have the gi of x less than or equal to 0 to be inequality constraints. Inequality constraints. Then you also have equality constraints. That's hj of x equals 0. And these are equality constraints. Okay. Now that takes us to the Karush-Kuhn-Tucker conditions, KKT conditions. So what are these conditions? So first of all, if X star is an optimal point, if X star is an optimal point, there exists there exist Lagrange multipliers, Lagrange multipliers, say lambda i's, okay? That is for inequalities, lambda i's for inequalities, and mu j's for equalities, mu j's for equalities, such that you now have the following. First of all, you can talk about stationarity. So you have a condition for stationarity. So, and what that simply implies is that the grad evaluated at that optimal point x star plus the summation all over all the i's of lambda I multiplied by the grad of, I mean, that's the derivative, right, of gi evaluated at x star plus the summation over all the j's for all the mu j's grad h sub j of x star that's evaluated at x star. All this is equal to 0. Okay? All this is equal to 0. Now that's more like the Lagrange expansion of whatever problem, of the problem we have stated above before now, okay? That's like the Lagrange expansion. But for stationarity, it says that when you have the whole thing out like that, then for stationarity, all of that expression is equal to 0. And then we go for the next point, which is the primal feasibility. Primal feasibility. When we talked about linear programming, we saw the idea of primal and dual. So you can transform, if you transform a minimization problem into the dual, it becomes the maximization problem and vice versa. So primal feasibility tells us that GI, talking about the inequality constraint, now GI X star would always be less than or equal to 0. And HJ X star will also always be equal to 0. So that's the primal feasibility. And then we go ahead to the next one, which talks about the dual feasibility. So stationarity, primal feasibility. Now we talk about dual feasibility. There are 4 of these conditions. So this is the third of them. Dual feasibility. Dual feasibility simply tells us that all the Lagrange multipliers, lambda i's, are always greater than or equal to 0 for every I. Okay, that is for dual feasibility. So very simple and straightforward rules. Then number 4, you have what you call the complementary slackness. Complementary slackness. So stationarity, primal feasibility, dual feasibility, and complementary slackness. What this simply tells us is that the Lagrange multiplier multiplied by uh the inequality constraints evaluated at x star is always equal to 0 for every I. So all these 4 conditions now are the Karush-Kuhn-Tucker conditions. So this one here now, this expression for complementary slackness, this ensures that either the constraint, either the constraint, that's the constraint gi of x, is active. So if the product of lambda I and gi of x star is equal to 0, so this ensures that either the constraint is active, meaning that gi of x star is equal to 0, or the multiplier is 0. So if their product is 0, it means that either lambda I is 0 or gi of x star is 0, basically. So these are the Karush-Kuhn-Tucker conditions, very simple conditions. Now, let's go ahead to take a problem that talks about feasibility. Okay, let me change over this time. Say now you have an example which is about convex optimization with feasible solution. Okay, with feasible solution. So that's what we want to see now. So uh imagine that we need to minimize f of x1, x2 equals x1 squared plus x2 squared, and that is subject to x1 plus 2x2 minus 3 equals 0. That's what we have. And then to deal with this, we can go step by step. We go for step 1. So for step 1, now we need to define the Lagrangian. Define the Lagrangian. Okay, so the Lagrangian is simply okay, I like to use this special L of x1 comma x2, and then since it is an equality constraint, right? So here we use mu, not lambda. Inequality constraint, we use lambda. So that means this is equal to xi squared plus x2 squared plus mu into, I mean, that one is already expressed in that way. If it is not, if you add 3 at the other side, you bring it to the other, to the left hand side, so everything can be together. So we now have x1 plus 2x2 minus 3, like this. So that is the Lagrangian easily. Then the next thing is step 2. So for step 2 now, we need to compute stationarity conditions. Compute stationarity conditions. So that means that we need partial L, partial x1, first of all. So we differentiate this with respect to x1. So the first one, we have the first one, x1 squared. Differentiate x1 squared, you have 2x1. So next, we have the next x1 is somewhere around here. Differentiate mu x1 with respect to x1, you get just mu. So this is plus mu. And this is equal to 0. That's the condition right there. And we can solve for x1. So we have 2x1 equals minus mu. So that x1 is equal to minus 1 over 2 mu, like that. So with that done, we can do the other one, which says that partial L, partial of the Lagrangian, partial x2 will now be equal to, so still looking at this now. So we have x2. So x2 squared, that's 2x2. We have 2x2. And then when we come here, we have 2x2 times mu. That should be 2 mu, right? So there we have plus 2 mu. It's plus, right? Yeah, plus 2 mu, 2 mu. And all of this is equal to 0. So we are looking for x2. So we have 2x2 equals minus 2 mu. So 2, if you divide through by 2, we have that. So x2 is simply minus mu. Okay. The first one is minus half mu, right? So we have all that. Now the next thing is is step 3, right? Step 3. So we have to solve for x1, x2 using the constraint, So what that means is that we have x1 plus 2x2 minus 3 equals 0. So And from that, we know x1 is minus half mu. So we have minus half mu plus 2x2. X2 is minus mu. Okay, that's minus mu. Then minus 3 equals 0. So we can have minus half mu minus 2 mu minus 3 is equal to 0. We can multiply through by 2. So we have minus mu minus mu minus mu minus 4 mu minus 6 equals 0. So we're looking for mu, right? So this is like so minus mu minus 4 mu, that's minus 5 mu equals 6. So that mu alone is equal to minus 6 over 5. Now that we have mu, we can easily take it back and get our x1 and x2. So okay. Well, we can, this is step 3, right? Step 3, we are solving for x1 and x2 using the constraint. So with that, now we can just say we have step 4. So for step 4, we can compute x1 and x2 finally. Compute x1, x2. So we already know that x1 is minus half mu. Okay, so x1 is minus half mu. That means minus half multiplied by mu, which is minus 6 over 5, minus 6 over 5. And that means that x1 is equal to 2 here is 1, 2 here is 3. So minus and minus is plus. So we have x1 to be 3 over 5. Done. And then we go for the next one, x2. So we know x2 is minus mu. So that is minus 6 over 5. And that tells us that x2 is 6 over 5. So with that in place, then we can verify the feasibility. Step 5 now. Step 5, verify feasibility. Is it feasible? Verify feasibility. Okay. So is this equality constraint satisfied with this particular condition? So let's check the equality constraint. X1 plus 2x2 minus 3 equals 0. Verify feasibility. That's check equality constraint. Equality constraint. That is x1 plus 2x2 minus 3. I mean, we expect that it would be right because that's where we even got it from. So x1 here is 3 over 5. We have 3 over 5 plus 2 into 6 over 5 minus 3. So if this gives us 0, then that means it is satisfied. So this is 3 over 5 plus 12 over 5 minus 3 over 1. So the LCM is 5. So 5 and 5 is 1. That's 3 plus 12 minus 1 and 5, 5. 5 times 3, 15. Okay, so this is equal to 3 plus 15. 3 plus 12, 15. 15 minus 15, 0. So we have 0 over 5. So we say, therefore, that's x1 plus 2x2. x1 plus x1 plus 2x2 minus 3 is equal to 0. Okay, so it means that the constraint is satisfied. We could actually take that for granted because that was what we got our value from in the first place. So since the equality constraint, is satisfied, the KKT conditions hold. The KKT conditions hold. And 3 over 5 over 6, comma 6 over 5 is the optimal solution, with objective function, If you remember, the objective function is f of x1, x2 equals x1 squared plus x2 squared. So that simply means that f of 3 over 5, comma 6 over 5 is equal to 3 over 5 squared plus 6 over 5 squared. So which is 9 over 25 plus 36 over 25, which is simply the same as 45 over 25. And that is 5 up there is 9, 5 down here is 5. So that's 9 over 5. Okay. So that's what we get there. So that is a feasible situation. Now let's take some um practice questions. Practice for feasibility of Kuhn-Tucker conditions. Okay. Of course, when the KKT conditions hold, which is stationarity, primal feasibility, dual feasibility, and complementary slackness, we can find an optimal solution. Okay, that's what this teaches us. By systematically applying the Karush-Kuhn-Tucker conditions, we can determine whether a constrained optimization problem has a solution, and if so, compute it effectively, just like we have done. So let's look at some practice questions. The first one is to solve the following constrained optimization problem using the KKT conditions. Okay, so minimize f of x1, comma x2 equals x1 squared plus 4x2 squared, subject to x1 plus x2 minus 2 equals 0. And the first question. So the second question is find the optimal solution. Find the optimal solution using KKT conditions. And that is to minimize x1, minimize f of x1, comma x2, which is equal to x1 squared plus x2 squared, minus 4x1 minus 6x2, subject to x1 plus 3x2 minus 9 is less than or equal to 0. And then we have x1, comma x2 greater than or equal to 0. That's the second one. So we go for the third, which is this, using Karush-Kuhn-Tucker conditions. I mean, use Karush-Kuhn-Tucker conditions to determine the optimal solution for this. Minimize f of x1, comma x2 equals x1 minus 1 squared plus x2 minus 2 squared, subject to x1 greater than or equal to 0, then x2 greater than or equal to 0, then x1 plus x2 less than or equal to 3. Okay, so please let me see the answers in the comments. either on YouTube or on Facebook. Coding, I don't think coding is necessary in this situation. The conditions are just straightforward. Then, of course, let me also know in the comment section how helpful these videos are for you. You can also let me know if there's a topic you'd like me to teach, a problem you'd like me to solve. Then, of course, because in the next video, I'll be talking about KKT conditions with infeasibility, where the conditions do not hold. So, as a result of that, you want to subscribe and hit the notification bell so you can always get alerted each time a new video is released. For those who have subscribed, thank you so much. Don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.